In this lecture, let us learn frequency compressive feedback FM demodulators. This is a very interesting variant of PLL which is often used for demodulating FM signals and more or less for the same purpose that the PLL is used. Okay, and in this we use frequency compressive feedback which is similar to phase locked loop, but there are some major differences. Now let us look at the block diagram. You have an input signal, that is your received signal. XR of t is equal to A times cos of omega ct plus phi of t, your angle. Okay, this is general angle modulator signal. Right, where phi of t is equal to 2 pi k suffix f times integral of m of tau d tau, like this. This is for your FM. In case Pm, then phi of t is equal to kp times m of t. Okay, now this input signal x suffix r of t is given to a multiplier. So I have a multiplier. I do not call it a phase detector anymore, because if you recall, in your phase detector you have a multiplier, then this is given to a low pass filter, but instead of low pass filter we are going to use band pass filter. So this one together is called a phase detector, if you recall. Okay, here I am going to use band pass filter. Okay, therefore the phase detector also has a multiplier, but that was followed by, look at here, low pass filter. So that to make the phase detector. But in our circuit, in frequency compressive feedback circuit, I will not follow it up with a low pass filter. I will follow it up with a band pass filter, and that may be very surprising for you. Now let us see how it works. Okay, now because this will not make sense if the carrier frequency, let us say here the carrier frequency is omega c, and in this point the carrier frequency is something else. Okay, so if both the carrier frequency are same, then it doesn't make sense, because if the carrier frequency in this point, let us say the point x and let us say the point y, then both are carrier frequency at omega c and omega c, then what you will get here? You will get either 2 omega c or 0 hertz. So the difference component will always be centered around 0 hertz. Some component will be centered around 2 omega c. So the band pass filter will serve no purpose. So it obviously implies that the VCO output is not at omega c. In the previous case, the VCO output is at omega c. If you recall, in the previous circuit, we said VCO output is let us say AB times sin omega ct plus theta of t, right? That is what we said in the previous case, and this is your A times cos of omega ct plus phi of t. But now in this case my VCO output is not at omega c, but it is omega c minus omega naught. Okay, so it is a different carrier frequency. The output of your VCO is not at omega c, but it will be omega c minus omega naught. So the output of my VCO will be omega C minus omega naught. Okay, whereas in the previous case, in the phase locked loop, the carrier frequency and the output of the voltage controlled oscillator, the lock conditions will be the same as that of the input signal. If you look at here, the carrier frequency is omega C and the VCO output also omega C in the previous circuit phase locked loop. But here in the frequency compressive feedback, the major difference is the output of your voltage controlled oscillator is omega C minus omega naught and the input carrier signal frequency is omega C. Therefore, the difference will appear here. Okay, so the difference will be omega naught will come and then 2 omega C minus omega naught will come, and let us tune your band pass filter to omega naught. Therefore, the output of my band pass filter will contain only at omega naught. So that means you are changing your carrier frequency from omega C to some other carrier frequency omega naught. Okay, therefore it is implied that voltage controlled oscillator works differently here. Okay, now what will happen is that you will have a signal here in the point X, you will have a signal here which is at some finite carrier frequency omega C, which will depend on the center frequency of the which will depend on the input signal. Okay, and voltage controlled oscillator produces the signal omega C minus omega naught. If you multiply, you will get omega naught and 2 omega C minus omega naught. Now your band pass filter's center frequency is tuned to omega naught. Therefore, band pass filter will allows this omega naught and rejects this 2 omega C minus omega naught. That is the main point that we need to understand here. And after this, what I will do, I will put it a frequency discriminator here. Okay, it looks like a strange, but let us see how it helps us. Okay, so I will follow it up with a discriminator again. It is a very intriguing kind of structure, and all kinds of questions should come to your mind when I drawing this will be answered quickly, okay, in a few minutes. So after this you will get a demodulated output. Demodulated output, this one, and this one you take feedback and apply here. So let's say this is my EV of t and output of my voltage controlled oscillator is E naught of t, right. So here the frequency will be omega naught comma 2 omega C minus omega naught, but here it will be in terms of omega naught. Okay, here the band pass filter has the center frequency of omega naught. This band pass filter has a center frequency of omega naught. So we will once again call the output of your voltage controlled oscillator as E suffix 0 of t, and output of your discriminator is EV of t. Okay, so there must be a lot of questions in your mind. See, I have phase locked loop. In addition to that, your frequency discriminator in this loop. And a natural question that will arise is, if I am going to use a discriminator anyway inside the loop, why should I have this device at all? Okay, why should I have this voltage controlled oscillator, then band pass filter, multiplier, all these guys? So we don't want all these things, right? Straight away you can give the XR of t given to the discriminator. What is your discriminator? Discriminator is a FM demodulator, right? So directly you can get FM signal, demodulated signal. Demodulated signal. Then why are we using this kind of structure? Straight away, if you have a FM signal, then if you give it to balanced discriminator that we discussed in one of the previous lecture, then I will get the demodulated output. Then if that is the case, then what is the purpose to use my multiplier, then band pass filter and voltage controlled oscillator and phase locked loop and all those things? I could as well straight away use the frequency discriminator and demodulate my FM signals. So you can ask why all these complications. Okay, so how this works and what are the advantages of the structure over the simplified discriminator. or issues, okay, that we will discuss in this frequency compressive demodulator. Okay, it has certain advantages, that is why we are considering this type of structures. Fine. So maybe let me draw the diagram again. Okay, so because one more time let me draw. You have the received signal XR of t. This is given to a multiplier output, let me call E suffix O of t, and this is given to a band pass filter. Band pass filter is tuned to center frequency of omega naught. So, and this one you have voltage controlled oscillator, then you give it to discriminator. Okay, so this is my E suffix V of t, and then like this. That's it. So this is my diagram now. Now if you look at what is the frequency at this point, carrier frequency omega c, because that is my received signal. Okay, and what is the frequency at this point? My voltage controlled oscillator is oscillating at the frequency of omega c minus omega naught. Therefore in this point my frequencies are sum of these two guys, sum frequency and the difference frequency. So you will get omega naught to omega c minus omega naught. These two components will be present here, and after the band pass filter it will contain only omega naught, and then you give it to the frequency demodulator, okay, discriminator. So this point let me call EV of t and En of t. That's it. This is my block diagram. So you have an input signal coming here, and this is followed by a multiplier, and followed by a band pass filter. Okay, this is slightly different from what we have discussed in the phase locked loop. Okay, in the phase locked loop, as I said, this multiplier is followed by a low pass filter, but here we are using band pass filter. So this combination, low pass this multiplier and band pass filter will act like a phase detector. But now with more or less we will do very similar thing, except that different signal will not be a baseband signal. In the previous case, in this the different signal will be a baseband signal. Okay, why is it baseband signal? Because you multiply this guy and that guy, AC times AV times cos of omega ct plus phi of t times sine of omega ct plus theta of t, cos A cos B, that is cos A plus B, AC AV by 2 cos of A plus B, that means 2 omega ct plus phi of t plus theta of t plus AC AV by 2 cos of A minus B, therefore phi of t minus theta of t. Now these two components are given to the low pass filter, and then low pass filter will remove this high frequency component, right? It allows only this portion. Therefore your output of your low pass filter here will be AC AV by 2 cos of phi of t minus theta of t, and this is my baseband signal. There is no carrier, look at here, no carrier. Therefore this signal is called a baseband signal. But in this case what will happen, this point is let me say AV times sine of omega c minus omega naught times t plus theta of t. So this is what coming out of your voltage controlled oscillator, and in this point this is AC times cos omega ct plus phi of t. Both are multiplied now. If you multiply both, then you will get AC times cos of omega ct plus phi of t multiplied by AV times sine of omega c minus omega naught times t plus theta of t. So this is equal to some component, some frequency component, AC by AV by 2. What did I do here? Cos A sin B, right? Sin A plus B plus sin A minus B. I am sorry, this is not cos. This is sine of sine. So here also this is going to be sine of A plus B. So 2 omega ct minus omega naught times t plus phi of t plus theta of t, some frequency component, plus difference frequency component AV by A2 sine of, it is going to be A minus B. So in that case omega naught t plus phi of t plus theta of t. And your band pass filter, look at this figure. This band pass filter is tuned to the frequency of omega naught. Therefore this component is passed through the band pass filter, okay, and but this component is centered at 2 omega c. Therefore this guy will be rejected. So output of band pass filter will contain this portion only, and this will be rejected. So in this point you have AC AV by 2 sine of omega naught t plus phi of t minus theta of t. That's it. So in the previous case we have the band pass signal. This is my band pass signal, but here you have a pass band signal. See, it is centered at omega naught. Therefore this is your pass band signal. Okay. So therefore the output of your multiplier will be the difference frequency between the incoming signal frequency and the voltage controlled signal frequency plus some frequency component. The moment you pass it through the band pass filter, you will get only the difference frequency component. Difference frequency component. The sum frequency component is located at 2 omega c. Okay. So therefore this 2 omega c component will be removed. And here the voltage controlled oscillator frequency is tuned not to omega c, but to a slightly offset from omega c. Therefore your VCO is tuned to omega c minus omega naught. That is slightly offset by an amount of omega naught. So there is an offset by an amount of omega naught. So that is the difference frequency here. Okay, this is my difference frequency. Sorry, this one is my difference frequency here. So in this point I will get a difference frequency. Okay. So in this point you will get a difference frequency. Some frequency will be eliminated. Okay. Now we will argue in this lecture that at the output of the band pass filter we again will have some kind of an FM signal. Why is it an FM signal? See, the input is A times cos omega ct plus phi of t. Here the carrier frequency is FC. But at the output of my band pass filter I have this signal, right? This is what I have at the output of the band pass filter. Now look at here, again I have carrier frequency, but now the carrier frequency is omega naught. Instead of phi I have phi minus theta of t, phi of t minus theta of t. So it looks like again like an FM signal only. So after my band pass filter again I am getting an FM signal, but the only difference is instead of omega naught I have omega, instead of omega c I have omega naught, instead of phi of t I have phi of t minus theta of t, and instead of sine I have, instead of cos I have sine term here. That's it. My original FM signal was AC times cos of omega ct plus phi of t, right? Now instead of omega c I have omega naught, instead of cos I have sine, instead of phi of t I have phi of t minus theta of t. But anyway again this resembles with the FM signal. But and the discriminator output is fed to the voltage controlled oscillator to close the loop. So the essential difference between the phase locked loop and the frequency compressive feedback system is that the voltage controlled oscillator is offset from the incoming signal frequency by an amount omega naught. Incoming signal frequency is omega c, and your voltage controlled oscillator output is offset by omega naught, that is why omega c minus omega naught. Okay, and as a consequence of the filter following by as a consequence of the filter followed by the multiplier is not a low pass filter, it is a band pass filter tuned to omega naught. Now how does this help us? To start the analysis of this, let us write down the mathematical equation and try to understand how it works, okay, what it is able to do for us. Now consider the signal, consider the received signal x r of t is equal to AC times cos of omega ct plus phi of t, where phi of t denotes your modulation. Now what is the output of your voltage controlled oscillator? I wrote here AV times sine of omega c minus omega naught t plus theta of t. So E naught of t is equal to AV times sine of omega c minus omega naught multiplied by t plus theta of t. Okay, some phase modulation this phi of t denotes. So once again the phase modulation theta of t will depend on the input signal here. Okay, so what I am saying is this theta of t depends on this guy EV of t. Okay, output of my voltage controlled oscillators, this signal, in this theta of t depends on the EV of t. Okay, so therefore theta of t depends on E suffix V of t, input voltage. How about this phi of t? Phi of t depends on what? Your message signal M of t. Okay, at the transmitter side your phi of t depends on the message signal in the modulator. Okay, so we know that the model is the model is that the instantaneous frequency is proportional to the input voltage. Okay, so here phi of t is equal to 2 pi kf integral of m of tau d tau. So by the same token theta of t also in 2 pi kf integral of EV of tau and d tau. Okay, so let me put all this constant by a notation kV and EV of tau d tau. So this is my theta of t. So instead of writing 2 pi, after all it is constant, right? So we least bother about the constant. Okay, so we just look at the concept. So I am writing this 2 pi kf as kv times integral of ev of tau times d tau minus infinity t. Okay, some constant. Okay, that is something called VCO constant, voltage controlled oscillator constant. So all the expressions are the same except that the VCO output is not at omega c but omega c minus omega naught. Okay, let's call the signal at the multiplier output as let me call ED. Let me put the notation ED of the difference. Okay, here this D indicates difference. Now what will be the nature of the signal ED? You multiply XR of t with this portion E naught of t. Okay, so this is my input signal XR of t. Okay, and E suffix d of t. So what is E suffix d of t? E suffix d of t equal to x suffix r of t times E naught of t. Now let us do the multiplication now. This already we did it, okay. So this is x suffix r of t and this is E suffix naught of t, and multiply, you will get two components. One is at 2 omega c minus omega naught plus theta of t plus phi of t, and another one is AC by 2 sine of omega t omega naught t plus phi of t what is this? This is minus or plus? It should be minus, right? Minus theta of t. So this is a straightforward application of your trigonometric identities. Now what will be the band pass filter output? The band pass filter output will be proportional to this guy. Therefore, if I look at the phase deviation at the input of the discriminator, what can you say about that? Phase deviation at discriminator input. So the discriminator input is nothing but look at the figure here. So this is my discriminator. The discriminator input is only the difference signal. Okay, so it is going to be 1 by 2 AC AV sine of omega naught t plus phi of t minus theta of t. Right? The phase deviation is not phi of t now. Phase deviation is phi of t minus theta of t. Okay, it is a difference between these two. So what it was in the case of PLL, there also it was phi of t minus theta of t. Here also it is phi of t minus theta of t. Okay. Now let us take this phi of t minus theta of t. This is equal to phi of t minus, what is theta of t? Just now we wrote a theta of t. Okay, theta of t is equal to in kV times integral of ev of tau times d tau. Okay, substitute here that one. Minus k suffix v integral of ev of tau d tau, like this. Okay, so this is being followed by the discriminator, And what could be the discriminator do, and what could the discriminator do here? The discriminator was not present in the PLL, okay, but here we have PLL. Sorry, we have a discriminator here. So in the previous lecture we did not have discriminator, but here we have the discriminator. So in the previous case we had a loop filter, but here in this case we have the discriminator here. And what is the job of the discriminator? It produces an output voltage proportional to the input instantaneous frequency deviations. Okay, so that is the job of frequency discriminator. So the output of the frequency discriminator is proportional to the instantaneous input frequency deviations. So this is my phase, therefore my output voltage is proportional to the deviation, deviation of this guy. This is my input deviation, input phase deviation, instantaneous phase deviation, input instantaneous phase deviation, and this one is given to your discriminator, and the discriminator produces an output voltage, and this voltage is proportional to the input instantaneous phase deviation. Therefore my output of the discriminator, so what is the notation that we used for output of my, it is EV of t, output is. So the output of the discriminator is EV, and that is proportional to your input instantaneous phase deviation. Therefore let us write down that EV of t is equal to 1 by 2 pi k suffix t, discriminator constant of d by dt, because you want output voltage, that is instantaneous frequency deviation, but this is my phase deviation, so you have to differentiate by that. So this 1 by 2 pi constant is coming because we are considering frequency, not angular frequency. So of phi of t minus theta of t. So this is 1 over 2 pi k suffix d, where what is your k suffix d? Discriminator constant. D by dt. D by dt is, let's say, d phi of t by dt minus d by dt of your theta of t. What is theta of t? Theta of t is this guy, kV times integral of EV of tau d tau. So that integration will go away. So let me write down, no problem. kV times integral of d tau. This 1 by 2 pi times kd is constant. So this is equal to 1 by 2 pi k suffix d. What is d phi by dt? Okay, let it be as it is, no problem. To d phi by dt, this is my EV of t times d phi of t by dt minus this differentiation and the integration will get cancelled. Therefore you'll get minus 1 over 2 pi kV times EV of t. Now rearrange this equation. So you take EV of t constantly outside, then you'll get 1 plus 1 by 2 pi kV and kd is equal to 1 by 2 pi k suffix d phi of t by dt. Therefore, your EV of t output voltage is equal to 1 over 2 pi k suffix d phi of t by dt whole divided by 1 plus 1 over 2 pi kV kd. Okay, now what is dphi by dt? Dphi by dt is the instantaneous frequency deviation of the input FM signal, which is going to be proportional to the message signal itself. Therefore, this is going to be what? M of t. So, 1 by 2 pi k suffix d whole divided by 1 plus 1 by 2 pi kV kd times M of t. So this is the output EV of t. Therefore, the demodulation is done. The output is proportional to M of t. This is my output. Output of what? Discriminator. Right? So discriminator output, which is nothing but your message signal, demodulated signal. So this is so therefore the demodulated signal is equal to some constant times that constant is this guy 1 by 2 pi kd divided by 1 plus 1 by 2 pi kV kd times your M of t. So your demodulation is done now. Therefore the output is demodulated signal is proportional to M of t. So very good job. Okay, so here I have taken the FM modulator constant to be 2 pi kf. That I did not add. Okay, so therefore this d phi by dt is, let me say, what is that, 2 pi kf times M of t. Okay, why this 2 pi kf comes? Because that's how it is defined. Okay, so what is, when we started the lecture, if you look at, yeah, phi of t is equal to 2 pi kf times M of tau and d tau. So from this, what is your d phi by dt? This is 2 pi kf times M of t. Okay, so this result we are going to use now. So in this I forgot to add here. So so instead of this d phi by dt, let me put 2 pi kf M of t, and this 2 pi and this 2 pi will get cancelled. Therefore your EV of t will be k suffix d k suffix f whole divided by 1 plus 1 by 2 pi kV kd times M of t. So I wrote wrongly previously. So therefore it is clear that the frequency compressive feedback system works as an FM demodulator. Frequency compressive feedback system works as an FM demodulator. So this is like your PLL, right? What is the difference? What is the big thing here? Okay, so what is the big question that you can ask? It works. Okay, fine. What is the big question? So there is a certain kind of question that arises here. Okay, if you are going to have a discriminator, like let me draw the diagram again. Band pass filter, you put a discriminator here. If you are going to put the discriminator here, anyway, you might as well just the discriminator and that will produce your FM output. So what have we achieved? To see that, let us go through some more mathematics, okay, a little bit of mathematics to understand why it helps or why it is useful to do this kind of analysis. Let's try to write an expression for the output of your discriminator. Okay, so let me call this point okay, let me call the output of my band pass filter as x of t. Okay, let us try to understand phi of t a little more. Okay, so I am defining a signal at the discriminator input. Okay, so x of t is a signal, input signal to the discriminator. Okay, so let us define what is x of t now. X of t is equal to minus 1 by 2 AV times AC sine of omega ct minus phi of t. I think I did a mistake in the previous calculation, minus theta of t. Simple trigonometric formula I did a mistake. Okay, so where is it? Yeah, so here cos a plus b, cos a sin b, then that is equal to sin a plus b minus sin a minus b. So this is not plus, okay, so this is going to be minus, so there is a minus symbol, so please remember this. And here the discriminator also you put a minus here, minus symbol. Conceptually correct, but accurately mathematical that is wrong, so you should put a minus symbol there. So this is my input signal to the discriminator, minus 1 by 2 AV times AC sine of omega ct plus phi of t minus theta of t. Now what is your theta of t? Your theta of t is equal to minus kV times integral of EV of tau d tau, and substitute this guy here. Minus 1 by 2 AV AC sine of omega ct plus phi of t minus kV integral of E suffix v of tau d tau. Now let us simplify these two guys together. How do you simplify? Is there a way to simplify this? Okay, we got EV of t. What is your EV of t? Just now we derived. EV of t is equal to 1 by 2 pi k suffix d whole divided by 1 plus 1 by 2 pi kv kd times d phi of t by dt. So what is your integral of EV of t? This is equal to, this whole thing will become constant. So 1 by 2 pi kd whole divided by 1 plus 1 by 2 pi kV kd, then integral of d phi of t by dt, and this integral and differentiation will go away, so you will get 1 by 2 pi k suffix d whole divided by 1 plus 1 by 2 pi kV kd times phi of t. So this is my EV of tau or EV of t in dt, whatever it is. Why I am making this kind of messy writing? EV of tau d tau. Okay, so this expression, what you do, you substitute here. Okay, so in the argument therefore this is going to be minus 1 by 2 AV AC sin of omega ct plus phi of t minus 1 by 2 pi kd, right, divided by 1 plus 1 by 2 pi kV kd times phi of t. Like this I can write. Now you simplify this. Here also you have phi of t, and here also you have phi of t. Okay, simplify that. Is it omega c? I am sorry, again I wrote wrongly. I am very sorry. So this one is omega 0, and this one is omega 0, and this one is omega 0. I am sorry. So this is equal to minus 1 by 2 AV AC sin of omega naught t plus, because this is a difference frequency, right? So your voltage controlled oscillator is tuned to omega c minus omega naught, and input to carrier signal frequency is omega c, so therefore the difference is omega naught. So omega naught t plus, if you rearrange these two guys, do some simple algebraic manipulations, then you will get 1 divided by 1 plus 1 by 2 pi k suffix d and k suffix v times phi of t. What is this? This is the input signal to the discriminator. Now let us try to look at this equation and get some kind of important points. Okay, now can we gain something? See, now in this case phi of t is multiplied by this guy 1 by 1 plus 1 by 2 pi times kd kV. Now this is the input signal to your FM discriminator. So the input FM signal was similar, but this is like, what is your received signal? X r of t is equal to a times a suffix c times cos of omega ct plus phi of t, right? Now instead of omega ct I have omega naught. Instead of cos I have sine function. Forget about this constant. Okay, this is not an issue. Minus 1 by 2 AV AC, and this AC is not an issue. After all, it is an magnitude of the signal. But now the beauty is, here I have phi of t, but here the phi of t is multiplied by this guy. Okay, so therefore let me call this is equation 1 and this is equation 2. So equation 1 is similar to equation 2. Equation 2 is my FM signal. Equation 1 also similar to equation 2, therefore this also an FM signal. Then what is the difference? The only the differences are, like here omega c, but instead of omega c I am using some other carrier frequency omega naught. Let us say this is 91.2 megahertz, and let me call this is some 50 megahertz, that's it. So some other carrier frequency, or 10 megahertz, not an issue. Instead of cos I have sin, that also doesn't matter. But what it matters is here I have phi of t and here the phi of t is multiplied by this constant. Okay, that constant was missing in equation 2. So the FM signal at the input or the PM signal at the input was sin omega ct, sin plus phi of t. Of course, we have different carrier frequency, but the carrier frequency is of no consequence, right? Because the discriminator will be designed to operate at the carrier frequency of the input signal, right? So it doesn't matter for the discriminator. So if you have directly used the discriminator, but the discriminator would have been designed around omega c, that's it. So the carrier frequency is not an issue. So you are using the discriminator inside the loop. If you look at the figure, so inside the loop you are using the discriminator, and this discriminator is working around omega naught instead of working at omega c. If you recall your discriminator from the previous lecture, like your discriminator is working at omega c if this is your input signal. Generally your FM demodulator is working at the carrier frequency, but now I am employing my discriminator in the loop, right? It is there in the loop. Therefore this discriminator is designed to operate at the frequency omega naught. So that is one difference. Now what is the other difference? The important point lies here. Let me delete all these guys so that I can explain one more time, because this is very important point. I want to stress here why this feedback compressive demodulator is used. Now let us look at this constant. What is the nature of the constant? 1 by 1 plus 1 by 2 pi times kd kV. It is a very small quantity, right? Is it a small quantity or a large quantity? It is a small quantity because 1 by some large value, 1 plus 1 by 2 pi, obviously kd and kV will be large. So it is 1 by large number becomes a small number, very small number. Okay, we typically choose very large values of kV and kd. So this will be large and this will be large. So what we are doing essentially is multiplying the incoming phase, this phi of t, by a small number. What does that mean? That means the discriminator that we are going to design for us within the loop, this discriminator that we are designing within the loop has to work with a narrow band FM. Okay, so essentially this equation 1 is nothing but a narrow band FM signal. Why is it called a narrow band FM signal? Because your phi of t is multiplied by very small number. Therefore your frequency deviation is much less than 1. As I said, if the frequency deviation is much less than 1, then it is called a narrow band FM signal. But here your original FM signal is wide band FM signal. So this feedback compressive demodulator essentially converts your wide band FM signal into a narrow band FM signal. Therefore the discriminator which you employ in the loop has to work with a narrow band FM signal rather than a broad band FM signal. So demodulating a narrow band FM signal is much easier than the demodulating a wide band FM signal. Okay, so even if the input signal is a wide band FM signal, because of this division, this 1 by 1 plus 2 pi, 1 by 2 pi kd kV of phi of t by a small constant, it converts a broadband signal into effectively narrow band FM signal. Okay, that means what? A signal with a small value of the modulation index beta. Therefore this equation 2 has beta modulation index is much less than 1. Okay, if you choose a large value of two constants, let's say kd is very large value and kV is very large value, then 1 by 1 plus 1 by 2 pi kd and kV is much less than 1. Therefore this small quantity is multiplied by phi of t this whole thing will be much less than 1. So your wideband frequency modulation signal becomes a narrowband FM signal. Okay, so because of this process, your phase deviation can be made small. So this reduces the bandwidth of the signal at the discriminator input. So this signal only you are giving to the discriminator to demodulate. Therefore, you need to have only a narrow band discriminator, that is enough. So the important point is, let me write down, for large values of k suffix d and k suffix v, the phase deviation can be made small. That means it implies reduces the bandwidth of the signal. There are other implications that we will discuss. Signal at the discriminator input. Okay, so effectively it reduces the modulation index. So modulation index of course talks about only for a sinusoidal modulation signals. So in general, basically it converts a broadband signal to narrowband FM signal. That means wideband FM signal to narrowband FM signal. So that's what I mean, it reduces the bandwidth of the input to the discriminator. Okay, so that's all about the frequency compressive feedback demodulator. Now you can ask me, like, why should that be important for demodulation? Okay, how does it help us? Because anyway you can design the frequency demodulator circuit for wideband FM and narrowband FM. So what is the thing that you are gaining here? Okay, so this has a very peculiar characteristics in the demodulation of FM signal. So that is the answer. What is that peculiar characteristics? Particularly when you are dealing with the noisy input signal. If your received signal is a pure FM signal, no problem. Pure FM signal, then you can use a PLL, no issues. But the received signal is not in the pure form, it is pure FM plus noise. In that case, it is advisable to use frequency compressive feedback demodulator. So in the noisy conditions, your frequency compressive demodulator will be very much useful. Okay, I mentioned this early very briefly. That is, the FM system works extremely well in noisy conditions. Okay, provided the signal is considerably larger than the noise. So signal strength, if is larger than the noise condition, then your FM is very good. Okay, that means the signal strength should be considerably larger than the noise. However, it is interesting to note, we will discuss how that happens later, but because we are not right now discussing the performance against noise, okay, we are not going to discuss now, we will do that little later. But as of now, what we do is, we will appreciate that the FM signal actually becomes very bad when the input noisy conditions becomes very bad. If noise increases, then FM system becomes very bad. If noise increases, implies. So instead of a graceful degradation, as the noise increases, which is what we normally expect, that any system to behave like that, right? As the input signal becomes worse, the output also becomes worse. But usually we would expect system to have graceful degradation. That means if you are bad, then I am bad. If you are good, then I am good. That is okay. But even though you are bad, but I am very bad, that is not acceptable, right? If A is bad, then B is also bad, no problem. But if A is bad, then B is very, very bad, that is not acceptable. Okay, so this is good. Okay, if A is bad, B is bad, okay, no problem. If A is good, B also good, okay, that also expected. But what happens after a certain time, if A is bad, then B is very, very bad. So that is what happening in your FM system. Typical scenario. Okay, now as the input signal degrades in quality. Degrades in quality means what? The noise is getting more and more. Okay, in that case, the output also should degrade in quality proportionally, right? If signal strength decreases gradually, okay, if input signal, I cannot say strength, signal quality. Signal degrades in quality, then the output also we expect that also degrades proportionally. But FM does not behave like that. It behaves extremely well when the input signal is good. See, if the input signal is very good, then it behaves very nicely. Okay, it behaves extremely well when the input signal is good. That is, SNR is good. If SNR is good, then FM is good. If SNR is low, then FM breaks down its performance. That means the moment the SNR becomes smaller than some specific value called threshold value, it starts to behave extremely badly. If SNR is less than some predefined value called threshold value, then your FM behaves very badly. Okay, and this kind of concept is called a threshold effect. It's a very famous question. Whenever you attend an interview, mostly they will ask this question, like threshold effect will occur in AM system or FM system. So this threshold effect occurs in the FM system, and it is advised to use FM always above the threshold value. So if the SNR falls below the threshold value, then your FM will be very bad. So we need to always use your FM system above the threshold value. That means what? The SNR should be high. Okay, so the SNR should be maintained to be larger than some threshold value. So this threshold effect is something we will discuss in more detail when we discuss the effect of noise a little later. So this is an important fact of life when we consider FM. Now this threshold effect that I have just discussed is more pronounced for wideband FM signal than for narrowband FM. So this threshold effect is very, very, more important for wideband FM than narrowband FM. So that is the reason we are converting our wideband FM signal into a narrowband FM signal using your frequency compressive feedback demodulator, right? So therefore the threshold effect is more pronounced for wideband WBFM, wideband FM signal than for narrowband FM signal. Okay, so this statement immediately gives us the motivation for going for frequency compressive feedback demodulation, because the discriminator here is working with a narrowband FM signal. So the implication is that it will be less pronounced. Okay, that means it is less prone to threshold effect. That means what? Your narrowband FM is less prone, P-R-O-N-E, prone to threshold. Okay, than the discriminator which would have had to operate on wideband input FM signals directly. Okay, the wideband FM is more prone to threshold. So this is a real advantage of going for frequency compressive feedback than your phase locked loop. Okay, so that is to reduce the incoming wideband FM signal to a narrowband FM signal. So we are converting the incoming wideband FM signal to a narrowband FM signal by using a multiplier, and then you put a band pass filter, and then here you put a voltage controlled oscillator, but here the voltage controlled oscillator is producing at omega c minus omega naught, and here the carrier frequency is omega c. Here you have two components, some component 2 omega c minus omega naught and then omega naught. So this output contains omega naught. So here what happens, your phase deviation is reduced such that your discriminator has narrow band FM signal. So the input is your wideband FM signal, and here in this point your signal becomes narrow band FM signal, because here phi of t is multiplied by a small value, that's why. So this is the real advantage of going for frequency compressive feedback. So what do we mean by the threshold effect is less pronounced? It means that basically the threshold is lowered. Okay, prone to more pronounced means more threshold. That's it. That's what we mean by. So the value of the threshold SNR at which it degrades disproportionately becomes smaller because of this frequency compressive feedback system. So in a way we carry out a kind of threshold extension using the frequency compressive feedback system. That means the threshold is moved to the left. Let me draw the figure. This is my input SNR, and this is my output SNR, my FM system. Now what happens, there is a linear relation like this. Now this is my input SNR. If the input SNR is good, my output SNR also good. Now again it comes here and this also good. But the moment it reaches, let's say this point is threshold point, then what happens, instead of reducing like this, it comes down like that. See, for this value your output SNR becomes going down negative, so the system becomes breakdown. Okay, for any communication system, if you want to plot, we have not yet done this analysis. Okay, so generally we will plot output SNR versus input SNR. Typically behavior would be like this, like a straight line. The behavior will be like this. And input SNR is decreased down in the left hand side. The output SNR also decreased like this. Okay, that is expected, right? So if the input SNR is reducing, then automatically the output SNR also decreasing. If the input SNR is increased, then that is expected, the output SNR is expected to increase. But there will be some SNR gain depending on what kind of system you have. But the output SNR will obviously decrease as the input SNR decreases. That is understood. But there is nothing wrong with that. Okay, if the input quantity is reducing, then obviously we expect that output quantity also will be reducing. That is not at all issue. Okay, that is likely to happen. But in FM system, what happens in FM system additionally, which is that, okay, as long as the input SNR is above some value, let's say in this region, no problem. Okay, so above some value, you will find the output SNR is very good. See, from this is my output SNR. Okay, it will be much more than what you can get in AM. But at the moment it falls below this value, the brown color, it falls below this value. Okay, the input SNR falls below, let's say this point is tau, let's say tau, below this tau point, then what will happen? Instead of degrading gracefully, okay, instead of degrading gracefully like this, this is graceful degradation. Instead of falling gracefully, it suddenly starts to behave like this, it goes like this, it goes like this. So this is breaking down, your system, FM system breaks down. It behaves extremely very bad. Okay, it suddenly starts to behave like that. The output SNR becomes much smaller than the linear decrease. See, this is my linear decrease, right? It becomes like this. So that is the threshold effect. Okay, so let me draw this curve one more time. So let's say input SNR and this one is output SNR. As long as you are in this region, let me draw this. If you are like this, no problem. Let's say tau. If you use your PLL, then it goes like this. Okay, this is for your phase locked loop. But if you use frequency compressive feedback system, then this threshold effect will be slightly moved to the left hand side. Then tau dash. Afterwards, it starts to break. Okay, therefore this one is for frequency compressive feedback demodulator. So if you use PLL alone, this is my threshold point. If you use frequency compressive feedback, your threshold point is moved towards the left hand side. Okay, at this SNR, this point of SNR is called the threshold SNR for your PLL. Okay, that means you have to maintain this SNR, at least you have to maintain this SNR. If the input SNR is above this value, you are fine. If the SNR falls below this value, what will happen? Your system will break. Okay, that's what we are trying to do in your PLL. But now, what we are saying is, if I am using frequency compressive feedback system, that means if I use narrow band FM discrimination rather than wideband discrimination, even though you are transmitting wideband FM signal, we are trying to move the threshold point, to the left hand side. So this additional margin I got because of my narrow band FM demodulation. So this narrow band FM demodulation is obtained by using your frequency compressive feedback demodulator or discriminator. Okay, let's say this SNR input SNR is 10, then let's say this point is some 6. So even if SNR is 6, then it will work. Just for typical value, some example value I am giving. So your tau dash is less than tau. So this tau is for wideband FM discriminator, and this one is narrow band FM discriminator. Here we are using frequency compressive feedback demodulator or discriminators, and here we are using PLL, something like that. Okay, so instead of this behavior starting at tau itself, it can start at the point tau dash, and you have the margin of tau minus tau dash. So and you are extending the threshold. So this is the purpose of your frequency compressive feedback system. So that is the reason we used that. So that is the main advantage of frequency compressive feedback system. So in one line, the advantage is it extends the threshold point. Point to the left. Okay. However, I am only making the statement here, okay, because I am not proved any of these things that I mentioned. So at this point we cannot do that also, okay. So this is the main advantage of your frequency compressive feedback system. So both the PLL and the frequency compressive feedback system essentially helps us to do this. So we need to have PLL as well as discriminator, but the only difference is instead of using a low pass filter, here we used a band pass filter, and your voltage controlled oscillator produces the frequency of omega c minus omega naught, but in PLL it produces omega c. Okay, so I think that this brings us to the end of discussion of FM demodulation using feedback circuits. So we discussed two feedback circuits. The first one is phase locked loop, and the second one is the frequency compressive feedback. So both have similar working principles, but they have different in detail. So that's what we have discussed now. Now in the next lecture we will talk about the performance of FM signals. Okay, so let me stop at this point. We will talk about performance of FM signals in the next lecture. Thank you.